Hello everyone, welcome to Rational Science. Why is it rational? Why do we call ourselves rational? Well, because everybody out there is irrational who tries to do physics or science. Why are they irrational? Well, they're irrational because they move concepts around during their physical interpretations. They transfer energy. They vibrate or excite the field. They move a charge. They move a mass. You know, all those are concepts. You can't move concepts around. And then the other reason is that a lot of people, or just about everybody out there, as far as I know, everyone out there, mediates everything with particles, discrete particles. And there is not a single phenomenon of nature that is invisible and intangible that you can explain in a rational manner with particles, with discrete particles. Okay? And here we do it with something else. We have elongated entities, which we propose. Those are the electromagnetic ropes, and those are going to mediate not only light, but gravity. We have what you could call the grand unified theory. It's not a mathematical theory, it's a physical theory. We have light and gravity in one mechanism. Okay? And that's the essence of this channel. Today we're going to talk about these so-called particles that quantum mechanics proposes. In fact, we're not going to talk about the particles. We're going to talk about something else. We're going to talk about the quasi or quasi or quasi. I call them the quasies, because I think you got to be crazy to believe them. The quasi-particles. Okay, so that's what we're the subject matter of today. If you're not interested in quasies, well, stick around. You might learn something. Stay anyways. Where do we start? Well, we have to distinguish the quasi-particles, from what quantum mechanics, I guess, refers to as the real particles, the authentic particles. You know, what's the difference? Well, if you go to the standard model of quantum mechanics, okay, you won't find a single quasi in there. These are crazy too, but I mean, you don't find any of the quasi particles in there, okay? And you say, well, why not? Shouldn't those be in the standard model of elementary particles? I mean, they're particles, right? So you would think they should be in there. Okay, so in order to see what happened here, you know, I want to show you today a little bit of history of how we moved from real particles, when in the old days people really thought in terms of real particles, real balls. Today they're known as classical particles, corpuscles, grains of sand, whatever you want to think of them as, such little beads. And from there we moved to quantum particles, okay, which are those over there essentially. And then from there we moved to the quasies, okay. So we're getting more and more abstract as we go along. So we need to understand what has happened here, okay. And a good way to start this is to see how we came up with these particles. I mean, where did these particles come from? And so let me give you a little history on this. Here it is. This is a chronology of particle discoveries, okay? And the first particle, I think you could say, for invisible, intangible phenomena. Remember, that's what we're looking at here. You know, the sandbox, we know. Sand, you can get a grain of sand in your hand, you can see it, you can touch it, you know what it is, okay? This is something different. This has to do with modeling, simulating the invisible, intangible world with particles, okay? And so since those particles are intangible and invisible, well, you know, they say these are particles. It's all mediated with these gazillions of particles that are all around us. And of course, the first particle was the photon. In other words, people even before 500 BC, they started wondering, you know, what is light, especially light? I don't think they had a notion of gravity yet. You know, they took it for granted, you know, things fall to the floor. I don't think anyone studied that at all, okay? Maybe I'm wrong, okay? But light is something that did concern them, and they said, what is light? And so the first thing that came to their minds is particles. Okay? And the particles that they invented in those days, or that they had in mind, came out of the eyes. It was the Superman theory of light. You know, Superman, he's got this X-ray vision. It's not that light comes to his eyes. Light goes from his eyes through the wall and sees the girl next door. Okay, that's the way it works. And yeah, for many years you had these people, first the Greeks, okay, and they believed that light came out of the eyes and went to the objects. The farther an object was away, well, the less you could see it, and at some point you couldn't see it any longer, like at the horizon. And so the light rays coming out of your eyes did not reach that far. That was the notion. It would be Alhazen, 10th century, and he came up with this notion that after studying light, he said, no, light comes from the objects to the eyes. Okay, so he reverted that direction, but it was still particles. It was all done with particles. That's what they thought it was. And that lasted even until the 17th century, when you had all these folks, and there are a whole bunch more. I'm just mentioning probably the most prominent ones, Galileo, Descartes, and Newton, and they believed in particles. Essentially, they didn't see a reason to change that at all. Robert Hooke, we don't have a picture of him because he was a deadly enemy of Newton, and he was also the right-hand man of Robert Boyle. And when Robert Boyle died, Hooke essentially was the caretaker of the Royal Society. And when Hooke died, well, Newton took over. For the first time, he became a member of the Royal Society, and he erased all vestiges of Robert Hooke, including his picture. So we don't have a picture of him today. But Robert Hooke was the guy who came up with the wave in his Micrographia book. I think it was 1665. He's the first one who mentions that light might be comprised of waves. And that was taken up later on by Christian Huygens, who went in there and analyzed it in more detail. But even in the case of waves, when Huygens and all these other people analyzed the wave, they were thinking of this. They were thinking of the ether, and ether was a bunch of particles, and these particles moved up and down, and they created this wave which was supposed to be light. Okay? In contrast, Newton held that it wasn't really that light, that the ether was waving. It's that something was traveling through the ether, again, particles, and they were traveling straight. So it was a question of straightness versus undulating. That's essentially what the fight between the wave theorists and the particle theorists was. It was straight versus, waving up and down. And again, Newton could not figure out how light could travel other than, in a straight line. Anyways, the photon was particles. Okay, it was essentially the first particle, and even to this day, it continues to be a particle in the eyes of all the mathematicians who vouch for quantum, and in fact for relativity as well, and for string theory. Okay, keep in mind, string theory talks about a line, 1D line. What is a 1D line made of? Well, it's made of zero-dimensional points. Okay, so what is each point made out of? Lines. And what is each line made out of? Points. It just goes on and on and on. Okay, so everybody essentially is dealing with particles. And it turns out that with particles, you cannot explain a single phenomenon of nature which is invisible and intangible, such as gravity, magnetism, or light. Okay, about 400 BC, we have Leucippus and Democritus, and these folks came up with the atomic theory. I don't know if they were the originators, but they're credited with it, and they came up and they said, look, the universe is made up of atoms everywhere, okay, especially anything that's got matter. They probably thought also that air and everything else was made out of atoms as well. That notion would last for hundreds of years until in 1876 we have this fellow, a German guy. He was a glass maker, and he came up with the cathode rays. Okay, that's what he named them in German. They were translated as cathode rays. But they didn't really know what those cathode rays were. It wasn't until Joseph Thomson, he came up with the notion that the cathode rays were made of electrons, and they called them negative, arbitrarily, I guess. And those electrons, as Thomson would theorize, according to mathematical physics, it's called proof. In rational science, we call it theorize. He was proposing, making an assumption, simulating, and saying that the electron was part of the atom, was a separate part of the atom. You had the atom and you had the electron. Okay, and the way he envisioned that was the plum pudding model, as it's known. He said there's this atom and it's got these negative. I guess you could call it fruits, embedded in it. That was his model. But he did think of the atom as being comprised of these negative pieces that fit into the atom as a separate, in other words, the electron was a separate piece within the atom. Okay. Rutherford would show, I show it as 1919 because that's when he wrote his paper, but he really didn't realize it until like 5 years later. That there was this thing he thought it was hydrogen atom, but it was really the proton, what he was thinking of. And he saw it as a particle. He thought that the center of the atom consisted of this main particle, which weighed about 1,800 times more than the electron, and that the electron was a bead that rolled around it. And that notion developed between him and Niels Bohr, a couple others as well. So they came up with this planetary notion of the atom. Now we had a proton particle, electron particle, and on top of that we had still our beloved photon. Okay, so we had these three particles. But it didn't stop there. Pauli, Wolfgang Pauli, in 1930, he came up with a notion of the neutrino. He was probably thinking of the neutron, because there was confusion at the time between the neutrino and the neutron. They had different functions, and he kind of mixed them together, and they said, "Oh, you proved this, but you were really talking about that sort of thing." Okay, and the neutrino wasn't proven to exist according to mathematical physics, proof, right, evidence, until many years later, 1956, Cowan and his partner, they allegedly proved the existence of the neutrino. Meanwhile, in 1932, Fermi comes up with the notion of the neutron. I think it was like mid-year. And at the end of that year, Chadwick ran an experiment and proved, again in mathematical terms, proved the existence of the neutron. Okay? Positron, we have the electron, this negative electron. This is a positive electron, otherwise known as the positron. Okay, we don't know what the difference is physically. All we know is this one carries a negative sign, this one carries a positive sign, because that's how they behave. If they're opposite, they attract, that sort of thing. And so that's why they put these labels, mathematical labels, that have no meaning whatsoever in physics. Okay, negative and positive. And so in 1930, Dirac came with the notion of his Dirac sea, which the sea which really formed space itself, the vacuum. And the vacuum was made of positive and negative particles that blended together, formed, I guess, nothing in his mind. Again, known as the Dirac sea. And for that, he created the positron. He theorized the positron. Anderson supposedly discovered it 6 years later. 33 also, Fermi came up with a weak force. He's the guy who theorized about it. That wasn't going to be discovered until 1983, way at the bottom, the W pluses, W minuses, and the Z bosons. Okay, so it took a lot of years to apparently prove their existence to the mathematical community, even though everybody believed in them throughout this whole time. Okay. 35, Yukawa discovers or theorizes the pi meson, and Anderson, and 1 year later the mu meson, they shortened that to pion and muon, two particles again of the standard model there. Higgs and about 100 other people in the 60s, they proposed the Higgs boson, the Higgs field. This notion was arising in the quantum community. Higgs wasn't the only guy. He just got the Nobel for it because I guess he was British, and they gave it also to Englert, another fellow who allegedly discovered it before him. So, you know, all that is just politics out there. There were a lot of others involved there. Anyways, the Higgs, supposedly one of the last particles to be included within the standard model. You will never find the graviton in there and never will. Okay? The graviton has not been discovered and never will be discovered except by virtue of the magic wand. They're going to force fit it in there if anything someday, but they have no way of showing the graviton. Okay? The graviton, for all practical purposes, doesn't exist, never existed, never will exist. Okay, and then we had the quarks. Zweig also said he had it before Gelman, and but Gelman got the Nobel Prize, and Zweig was a little ticked off about that. Okay, he wasn't even considered, even though he says he came up with a quark. Politics again, and then the Germans, Deci, they discovered the strong force, the gluon, 78, 79, even though it was, again, theorized a long time ago. And that essentially completes the standard model. So here it is one more time. Okay, let me put it up here. Okay, that's what we have there. And you can see there are no quasies, no quasi-particles in there. All we have is these particles that form part of the standard model. Okay, so how is this any different than the quasies, the quasi-particles, quasi-particles, or whatever you want to call them? Well, you heard of Quasimodo? You know, he's this ugly guy who crept up a church, a cathedral, the Notre Dame Cathedral in France, and he fell in love with this beautiful girl, okay? And he swept her off her feet, in a sense. Here, let me show you what I'm talking about for those of you who don't know the tale, okay? Here it is. Okay, that's Quasi there. And he climbs around, you know, he's going to save the girl, you know. She was facing the gallows there, and he's going to sweep her off her feet and take her away, save the day. Okay, so yeah, why do I mention this fellow? Well, I mention him because you say, why was he called Quasimodo? Well, it turns out that you might think he's half a man, or maybe like a man, or not quite a man, maybe halfway between man and beast, or whatever. He had this hunchback, he had, you know, this his eye, or whatever. No, he was named Quasimodo because he was, when he was born, parents realized he was born so ugly, so out of whack, that they decided to turn him over to the church. So they left him in a little basket at the door of the church and left. And they said, let the church worry about this guy. And they did it on Quasimodo Day. They did it, or I think it was the day before, they left him at the door of the church. And here's what Quasimodo means in Latin, okay? And it's the Sunday, it's the Sunday after Easter, okay? And it comes from Quasimodo, and the first words of the introit, which is the entrance, okay? The priest comes into the church, okay, on that day, and it's this entrance. It's called the Quasimodo Geniti Infantis, okay? And what does that mean? Well, it means as if a newborn babe. Okay, so you enter the church and you kind of enter as a babe, and that's how Quasimodo entered there. So it means, the important part here is the Quasimodo. You know, Quasimodo means as if. And so they use this quasi or quasi, again I call it quasi in the case of quantum, as a kind of like. Okay? It's not quite, but almost there. Okay? So in the case of the quasi or quasi particles, we're talking about something that's in the process of becoming a particle. It's not quite a particle. It's trying to make it to be a particle. It's trying to graduate into a particle. Okay? And you might say, well, when did this start, this quasi particles? Was this something recently? Turns out that, we had our first quasi in the 19th century, in the early 19th century. And it was this fellow here, and his name was Russell. He was a shipbuilder, and what he did was, one day he was watching how a ship came in. Remember, you're talking about wooden ships. Okay. Ship comes in and docks, but as soon as it kind of slowed down and stopped, he found that the wave that it created continued rolling by. And he was on a horse, and he chased that wave down. He went along the bank of the river and just watched it all the way because it caught his attention. And he found out that this wave just kept rolling along. And he called it a wave of translation and wrote about that. He even built in his garage, he built a little device that created waves and studied waves. Okay? He called them wave of translation. And that wave of translation is going to become, in the 20th century, going to become this soliton. Okay? And that's the first quasi that we have on the books. Okay? And what is a soliton? Well, it's a self-reinforcing wave packet that maintains its shape while it propagates at a constant velocity. And here you have a couple examples. There's more examples of this soliton wave. And it's a fascination with a lot of these mathematicians. They study it, they get equations on this, they study them from every angle. For them, it's a big thing. We have no use for these things in science, in physics. Maybe explaining them, that's where the scientific part stops. But we don't go beyond that. They're nothing more than curiosity. That's it. And that happened in the 19th century, but nobody thought about these quasi-particles, or solitons or whatever, until the 20th century. After the mid-20th century, you have this fellow. He's a Soviet scientist, Soviet mathematical physicist. Okay, he worked on the Soviet bomb, and his name was Lev Landau. 1956, he has to invent the quasi-particle. Okay, for the first time. He brings it into the vocabulary. Okay, so what is it? Well, he used it to explain a theoretical model of interacting fermions. Okay, and these quasars describe the normal state of most metals at sufficiently low temperatures. In other words, you're talking about, again, collective motion, and he's going to apply this to liquids and to metals. Okay, and his theory explains why some of the properties of interacting fermion systems are very similar to those of ideal Fermi gas. Okay, that is, non-interacting fermions, and why other properties differ. And Landau reasoned that what interactions do is to produce virtual particle hole pairs. Where did he get that? Well, he got it from Mr. Dirac. Where they were dealing with all these particles and holes and positive and negative coming together and forming this background. And he applied that notion, the same notion that Dirac had for his C. He applied it to solid state. He's applied it to several parts of what they call mechanical and electrical physics. Okay. So what came out of all that? Here's a definition first of quasi, as I call them. Just so you know, I'm repeating this from last time. Quasi-particle is a collective excitation. They're emergent phenomena. When you have many, for example, atoms or molecules or photons or electrons vibrating in a given way, well, they call that collective excitation a quasi-particle. That's all it is. They call it a particle. That behavior, that collective behavior is called a particle. And there you see an example at the bottom. Just one example, by the way. I've shown others the other day, so you can check on the previous videos. You'll find some other examples. Okay? And from that, they came up with all these list of quasi-particles that, to this day, all the mechanics of quantum, everywhere in the world, this is what they do. This is what they do for a living. They study quasi-particles. They've forgotten about the standard particles, about the atom. They learn that in kindergarten physics when they're getting their masters. That's kindergarten physics. You know, what a proton is, what an electron is, what a muon is, a pion. They left that stuff behind. Now they've evolved, and now they talk about what? Quasies. They're into the quasi world. Why? Because they get a job somewhere. And usually they get a job in a manufacturing place, either as an engineer or to study or to develop or some product. And so they go in there and they try to study behavior, collective behavior of particles. Okay? And so they gave names to all these behaviors because this guy studies this thing, this other guy studies that other thing. And what happens out of this, they had to give them names so that they could put them in their writings. You know, they publish papers and they said, well, what are we going to call this? Well, we'll call this quasi-particle this. And the other guy says, I'll call it that. Okay, and so they have all these different names for these different quasis, okay, or quasies. And here's a list of them, okay. There's probably more of these out there. I'm mentioning probably 90% of them probably, and again, I must have missed a couple here and there. This is what the standard model of quasies looks like, okay. You've got all these so-called particles, and what they are, they're all collective excitations of something, okay. In fact, look at the last one, the wrinklon. It's got to do with wrinkles, okay? And you'll see some of them like the orbiton there. You know, it's got to do with orbiton. You got the oscillon. It's got to do with oscillations, okay? What other one can we mention real quickly here? Perhaps the, what is it? The plasmon. Got to do with plasma, okay? So these are the particles that these people study, and they're not really particles, they're collective excitations that they go into the lab, they can't see or touch what they're analyzing, and so they theorize about it, but then they introduce the word proof and exist and evidence. They introduce these words because they say, we've proven it, we found, we discovered. Because they got to get their Nobel or their Wolf Prize or whatever prize out there, and they say, look, we did something for humanity. We discovered this particle. Well, did you discover like a particle, like a little bead, a little grain of sand? No, it's not even close, because we're not even talking about a quantum particle that's in the standard model. We're not talking about a little ball, which is not a ball even there, in that case. They're talking about an excitation of many particles. And that's what all these particles are, excitations of many particles. And let me go through some of these just so that you get a feeling. Okay, I'm not going to go through all of them, by the way. I don't want to bore you to death, but I want you to get the hang of what these people are up to, what you're paying for, because these people rely on government funds in almost all cases, either directly or indirectly. They depend on grants, and also on rich people contributing to their specific pet projects. Okay, so there's a lot of money going into this research into quasis. Okay, and here's I'll just review real quickly here. This is the phonon I presented the other day, and there's several types of phonons. You can see there, each one of these vibrations is a different phonon. So You got work there, job security for lots of so-called physicists, mathematical physicists, who study each one of these different types of vibrations. Okay, and those are the phonons. Those are people who specialize in phonons. Okay, I mentioned this. This is probably an even more important field, which is the holes. Okay, and I showed this the other day, where you have the holes going in from to the negative pole or negative terminal of a battery. Why? Because the electrons, the negative electrons, are going in the opposite direction, leaving a hole in the valence band of the atom, and that movement of the hole opposite of the electron bead, that's flow, is considered a positive current. Okay, so that's how this came about. And again, this is important in the semiconductor business, which I worked on quite a bit, because of this. Because what happens when you put a p-type and an n-type crystal together, they form what is known as a depletion layer, and the electrons allegedly go through the barrier and neutralize those atoms. Okay? So it creates this neutral region known as a depletion region. And so this is important in semiconductors, and it's one of the things I want to mention today, and that's got to do with the fact that all these so-called quasies, they have to do not with science, they have to do with technology. Okay, that's why they're important, because people don't care if you understand the invisible world out there. They don't care if you can explain it in a rational manner. That's out the door. They don't even care about that anymore. What they say, this is how we're going to explain it, but that's not important. The important thing is to discover the behavior, whatever behavior you're studying, giving it a name, always ending in on, okay? It's got to be on to be a particle, okay? And you give it a name, and you study it, and you use it for something. You don't understand it any more than Edison understood electricity, what electricity is. He didn't need to know that. He just needed to develop the filament for the light bulb. And so, because he was working on developing a gadget. So he doesn't need to know what electricity is or how to explain it or anything like that. He didn't need to have a physical interpretation for electricity. What he needed was to develop a gadget. And so they said, well, you send electricity here, you produce this effect, and it creates light. And that's what we need to sell out there to the people and make our company and the investors richer. That's all it was about. And this is no different. These are people who are studying semiconductors in the case of holes, right? And what they do, they study, the semiconductor, but they don't understand what's happening there in real life. They simulate it always with particles, because that's the easiest thing to put an equation to. You can describe it with an equation much better if you've got a particle than, for example, an extended entity like we're proposing, such as a rope. Okay? So that's how the particle keeps having an everlasting life. It never dies, because it's easy for the mathematicians to deal with particles, because they can put a value, for the point particle, for whatever value it's got, they can put that in the equation. Okay? So this is the issue. They don't understand it, but they don't care if they don't understand it or not. The important thing is, can you develop a gadget that makes us money? That's what it's about. Okay, so let's go through a couple of these. Here's the anion, okay? And just go alphabetically through a couple of these just so you get the hang of it. What is this? Is it some kind of bean? Is it some kind of grain of sand? A little pearl of some kind? No, it's a type of quasi, right, that occurs only in two-dimensional systems. Two-dimensional system. What the hell? I thought two-dimensional was outlawed in our real world. And these people say the anion only belongs to two-dimensional systems, which is going to give you an idea that they're talking about maybe geometry, for sure mathematics, for sure guaranteed, not physics. In a two-dimensional world, two identical anions change their wave function. They change their wave functions. Like if a wave function is something you change, you trade or you exchange or throw away or a kick or a jump or whatever. When they swap places in ways that can't happen in three-dimensional physics. Okay, so now we move from three-dimensional physics to two-dimensional physics. They are going to use this anion. This process of circling one particle around another is referred to by its mathematical name as braiding. Okay, they call it braiding. Okay, so that these things are going to twist around each other. Sounds like this, like a rope. Braiding, maybe. Okay. Braiding encodes information in a more robust way than other potential quantum computing technologies. So what does this have to do with science? No, it's got to do with technology, with gadgets, with inventing stuff. Okay. Not a billion anions were detected by 2 experiments in 2020. Did they detect a particle? No, they detected a behavior, a collective behavior of many particles, and they call that whole behavior, which is more or less localized because they're talking about a microscopic world, and they say, oh, it behaved in this way, we're going to call that what? An anion. Okay? And not a billion anions have not been definitely detected, although this is an active area of research. Okay, so this is what you're paying for. You're paying for these people to do research and development on two-dimensionals things, non-physical, okay? So that means they're just going to describe it mathematically. And what for? For technology, not for science at all. It has nothing at all to do with science or physics, but it's included within mathematical physics, and it's a very strong area of research, okay? Okay, let's continue here with the next one on the list. Again, I'm just going to go alphabetically through a couple of these just so you get the hang of it. This is the Bion. Nothing to do with sex, okay, just because it's got the prefix bi in there. The bound state of 2 solitons. You remember what a soliton was? It was a wave, okay? Somehow it became a particle. And they take 2 solitons, okay, and they say if these two have a bound state, they're kind of interlocked. Maybe entanglement. One soliton somehow affects another one from a distance. We don't know how or why. We don't care because we're just doing technology, right? Or in systems where the bound state periodically oscillates. A breather. Okay, what's a breather? A nonlinear wave. Somehow the particle converted into wave, wave goes to particle. That duality, okay, that comes in handy. Okay, annoying for them because you'll never find a wave in the standard model, in which energy concentrates in a localized and oscillatory fashion. There it is, in a nutshell. Then we have the bipolaron type of quasi. Okay, quasi consisting of 2 polarons. You don't have one, we have 2. Okay, so what's a polaron? Well, it's a quasi used in condensed matter physics to understand the interactions between electrons and atoms in a solid material. Okay, so we're talking about interactions here. They call that a polaron, then they take 2 polarons, which is 2 interactions, and they're going to have a what is called a bound state, which is essentially action at a distance entanglement. That's essentially what they're talking about. Between particles, no, not really particles. They're between electrons, but they're not talking about an electron anymore, or a positron or anything like that, a discrete particle, which is not a particle to begin with, but they're talking about the excitations of many of these particles. So they have a bunch of excitations here, which is a wave. We have a bunch of excitations over here, which might be a field or a wave, who knows what it is. And if they're kind of bound to each other, entangled, action at a distance sort of, this one affects that one, who knows how, by magic, then they're going to call that a bipolaron. Okay, so this is how it goes. And what does a polaron do? Well, it describes an electron moving in a dielectric crystal. I mean, we're not talking about an electron, we're talking about the motion of an electron now, okay? Okay, let's look at another one here. Okay, just going down for a couple of these so you get the hang of it. That's all I'm doing here. And they invent these strange names. Let's see if I can pronounce this thing. Bogoliubon. Bogoliubon. Okay, it's a quasi that occurs in superconductors. What are we talking about? Are we talking about science, Physics? No, we're talking about technology, gadgets, things, inventions, okay? Where superconductivity is characterized by a condensation of Cooper pairs, which you see at the bottom there, in the same ground quantum state, Bogolyubov, because it's got both names, Bogolyubov and Bogolyubov. I think it was because it was a Russian who invented this stuff. Quasies are elementary excitations. That's what they are. Above the ground state, okay, like an excited state of an atom, that you have the ground state and you have the excited state, and this is above the ground state, okay, which are superpositions, okay, of the excitations of negatively charged electrons and positively charged electron holes. Not positrons. These are holes, which are the absence of electrons. Because they have the absence of electrons, they're going to call that positive, and they're going to have superpositions of these vibrations, excitations. I mean, I lost track by now, you know, what they're talking about. And they're going to call these Cooper pairs, and this is what they're going to use the Bogolyubov for. They're going to say it's a quasi-particle. It's an excitation of elementary. It's an excitation of elementary excitation. That's what it is. It's pure excitation, excitement all around. That's all this stuff is. What's a Cooper pair? A pair of electrons bound together at low temperatures. So they're going to take these electrons, they're going to freeze these things, they're going to see what kind of vibrations they have. They're going to look at the holes that are vibrating, vibration of holes, which is the absence of an electron, which is, again, you take the electron out of the valence band and somehow something remains vibrating in there. And it's not localized, it's just a bunch of vibrations of nothings, of the absence of electrons. That's what the Bogolyubov has to do with. That's what you're paying for. I might need a beer after this just to get my sanity back, okay? Well, if you ever wanted to ask, here it is. I finally found it for you. Okay, here's the answer. You always wanted to know what a configuron was, right? You know what a configuron was. It's elementary configurational excitation, another excitement, okay, in an amorphous material technology, which involves breaking of a chemical bond. Okay, so we have a breaking of a chemical bond. It creates some kind of excitation, and that elementary configurational, excitation, that's going to be called a configuron. That whole thing turns into a particle. Now, what sense can that possibly make in science and physics in trying to understand how this universe works? Absolutely none. Okay. And then we have the Dislon, obviously, we learned this in kindergarten, right? Localized collective excitation, another excitation, bunch of excitation associated with what? Dislocation in crystalline solids. Okay, so you have a dislocation, something out of place, and we'll call that a Dislon. Okay, what's a fracton? Well, that's a subdimensional particle. You know, you have dimensions, and this is like a quarter of a dimension. What's a dimension? Dimension is direction and orthogonality. That's what a dimension is. Okay, 3-dimension, you say the table is 3-dimensional. What do you mean? It's got length, width, and height. And these guys partition the dimension. They cut it in half. They cut direction in half. They have half a direction, maybe a quarter of direction. So they call it a fractal or a fraction of a dimension. That's what a fracton is. It's an emergent topological crazy excitation. They're all excitations. They get excited about all these things. A collective quantized vibration or excitation or movement, jumping around back and forth. Okay, that's what it is. Oscillation, which is immobile when in isolation. So the only way it can move, vibrate, is when you put it with its buddies. When it's isolated, the fracton doesn't move. It doesn't vibrate. There's no excitement. Fracton has no excitement when it's alone. Then don't forget the very important holon, okay? Also known as a charge-on. Why? Because it comes from hole and charge, right? One of three quasies, along with spinons and orbitons, okay? Those are very important particles, okay? You gotta have them for the test on Friday, okay? That electrons in solids are able to split into during process of spin-charge separation. They're going to take the spin away from the charge, if that makes any sense to you. Here we have two concepts that belong, for example, to an electron top. The top is spinning, and we're going to take the charge over here and the spin over there because they part company. Yeah. Whatever that means in mathematics. When extremely tightly confined at temperatures close to absolute zero. Yeah, they're studying a lot of this stuff, what happens to materials at very low temperatures. Because they want to see if they can develop these, supercomputers, as they call them, or quantum computers. And what they're going to be doing is they're going to freeze them. They're going to bring them down to very low temperatures to see what kind of effects they have. They have maybe less resistance, maybe not as much heat in the little chip, so they can make them smaller. See, one of the problems you have with semiconductors, the smaller you make them, the geometries are closer together. And so they heat up. And you can't make them any smaller because they heat up even more and more and more, and finally they melt. But what if you were to cool them down and freeze them? Well, then you can get into this quantum computing, this super cool world. Okay, that's what it's all about. It's about developing technologies. Do they understand what's happening in that invisible world? Absolutely not. They simulate it with particles because that's where they can apply their equation. They can put that number in an equation. But then they're not interested in the physical interpretation. All they're interested in is what effect does it have, and can I use it for something? Can I make something out of it? Can I invent something? Can I make money? That's what it's all about. That's why there's investment in that world. That's why so many of these so-called physicists, mathematical physicists, mathematicians is even a better one because they do all their explanations are magical, and they claim at the end of the show that they don't understand, the quantum world. Of course not. Not if you're going to simulate it with particles. You'll never understand it because there are no such things as discrete particles. You would not be able to explain action at a distance with particles, much less can you explain them with quasies, because quasies are localized vibrations of many particles which they turn into a single particle, and they call that a quasi. Quasi this, quasi that. They're all quasi. Okay, here's maybe one of the last ones I'll mention here, okay? This is the exciton, okay? How's that for a particle name? I mean, if they're all excitations, I'm sure the exciton has to be the number one particle, What is it? It's a bound state of an electron and an electron hole. So these things are bound. When you hear the word bound, it doesn't mean bound. Like nothing in mathematical physics is what the word says. Spin is not spin, particle is not particle, and bound is not bound. Bound does not mean that it's tied like, by a string or a wire or a cable. That's not what bound means. Bound means that action at a distance by magic. That's what bound means. Bound means entanglement. This particle does something, this one follows suit and imitates it or acts in the opposite direction or whatever. In other words, it responds to this one through magic, only through magic. Magic wand, okay? It's done through magic. It's called black magic. They don't understand it, they just say it does so. We've proven it. Here's the equation, and we saw it we observed it in the lab. Did they observe whatever happened in between, the mechanism? Absolutely not. They cannot explain that at all. Okay, so it's important to understand that. Okay, it says an exciton form when material absorbs a photon of higher energy than its band gap, and so on. Well, you can read that later on. Again, all these quasies, they have nothing to do with science because You cannot explain any phenomenon of nature, any invisible phenomenon of nature, just by saying that it's an excitation of many particles. Okay? I do want to mention one last one, only just to rub it in. Okay, here it is. I think it's this one. Yeah, this is called the Dropleton, which are droplets of electrons and holes. Why do I mention this one? Well, I mention it because I just want to show that this is a formal paper written on these Dropletons. And what these people are saying, as you can read it here, is that it's got to do solely with technology. And let me just read here what's in that red box there. Building blocks for more complicated structures. It is often possible to incorporate interactions in theoretical treatments of crystalline solids by introducing suitable quasi-particles that have an effective mass, spin, or charge, which in turn affects the material's conductivity. That's what they're interested in. Optical response or phase transitions. Additional quasi-particles interactions may also create strongly correlated configurations yielding new macroscopic phenomena. In other words, they're interested in the phenomena, in the behavior. They're not interested in the explanation, such as the emergence of a Mott insulator superconductivity or the pseudo-gap phase of high-temperature superconductors. In other words, they're interested in technology. But see, the interesting part is that they mention the exciton, the bi-excitons, and the poly-excitons. And they talk about the existence of these particles as if taken for granted. Of course, they never define the word exist in physics, so we don't know what they're talking about when they say exist. But look on the right-hand side there, the box in red again. It said, we present experimental and theoretical what? Evidence for the existence of quantum droplets in an electron hole plasma. So these people are claiming that they've proven the existence and they present evidence, which is what mathematical physics is all about persuading your colleagues that you found it, that you discovered it, so that you get some kind of prize or recognition or whatever. And that's what it's all about. It's like saying, we saw something in the lab. What did you see? Well, we saw, what was it, a Dropleton? What do you mean you saw a Dropleton? What is a Dropleton? What's a blah, 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 blah? Okay, yeah, I understood that. And what are they talking about? They're talking about a behavior, collective behavior. And why is it important? Well, it's the only relevance of it is in terms of physics, of technology. That's all they're interested in. They're interested in technology, and if you can develop some kind of gadget with it, or make something more efficient, or you can run it maybe at colder temperatures, or faster, or longer life, or any of those things that you can improve on an existing device or gadget or whatever, then for them it's worth a lot, because that translates into money. It's part of the research and development of a lot of companies. So there's no problem there. I just want you to understand that it's got nothing to do with physics. Physics is about explaining, about understanding what's going on in that secret world. If you're going to dismiss the explanation, the physical interpretation, say, I described it, I saw it, I observed it, I called it, I gave it a name, fancy name, okay? Yeah, and it does this, and it's going to save so much money, or it's going to create a faster device that we can sell much better than the competition, and so it's going to earn the company money. Well, yeah, all that's got to do with business, with developing, research and development, with manufacturing, that sort of thing. It's got nothing to do with explaining how Mother Nature runs her shop. It doesn't explain anything about electricity. It doesn't explain anything whatsoever about how magnetism works, how gravity works, how light works, how the atom works. That's where it fails. And that's where it's misleading, because a lot of people say, what do you mean the mathematicians don't understand, that they cannot explain, that they don't understand quantum mechanics? We wouldn't have all this technology if they didn't understand. Well, no, it's because experiment and technology have nothing to do with science. You can do an experiment. What's the purpose of the experiment? Either to reinforce your preconceived beliefs, notions, or that of others. An experiment is used to convince people. It's used to persuade. That's the only purpose of an experiment. It's that you satisfy yourself that whatever theory you have in your mind, you confirmed it with that experiment. And you haven't convinced everybody else, but then you go to the court and you show it to the jurors, and you say, look, here's an experiment that proves my theory. Proves. And I proved the existence of the plasmon or the bion or any of those particles there, bipolaron. I proved the existence because, look, here it is. And see, you see that vibration? That's the polaron. That's how it works. An experiment is only used to persuade people. I mean, you can run any experiment you want at home. When you come to the conference, we need for you to explain what you understood or how it works. You need to explain the mechanism. If you're just going to tell me a description, say, yeah, a chair has 4 legs, well, that's not much of a science, you know. And this is what these people are doing. They say, we observed. What did you observe? Well, we observed these vibrations, these oscillations, these excitations. And we gave it a name. We called it the what? Bipolaron or the phonon. Oh, okay. And what does the phonon do? Well, it makes you a lot of money. Oh, okay, then I like it. That's what it's all about. Where's the explanation for what's happening in that secret world, in that invisible world? For that, you need a mechanism, and for mechanism, you need what? You need objects. You need to do them with things. For that, you need to know what a thing is. Okay? Anyways, this is what I'm proposing. Okay? I took the trouble to put them, you know, like Mendeleev did with the standard, with a model of chemical elements. Okay? And I did something similar with the quasies. And I put them there so that I hope I get credit for this, you know, somewhere. And while I was doing this, I did my own research. And don't laugh at me, but, you know, it took me a whole week. I was watching day after day. I think I'm coming back. Okay, I'm reconnected. Anyways, I was watching my curtain for a whole week. Okay? And this is what I saw. I found an excitation one day. And because of that, you know, I call this excitation, this collective excitation of the cloth, and I called it a phantom. But, you know, because of the rules, the laws of quantum mechanics, I had to change the name to a phanton because everything has to end in the letter N. Okay? So there you have the phanton. That's my contribution to the quasies. Okay? And all the others are there in nice, neat fashion so that you can locate them. They don't belong to the standard model of elementary particles. They belong to the standard model of quasies. Okay, so I hope I get credit for that. Okay. Anyways, here's my conclusions on the quasies. Okay, you can take this to the bank. Okay, quasies are not particles. They're not corpuscles in any sense of the word at all. Why they use the word particle to mislead you, I have no idea. Maybe it's just for that, just to mislead you to think that they're doing physics when they're not. Okay, they were invented for what? For inventions. So they have an invention for an invention. What's the point of it? Technology, making money. That's all it is. Its interest is only in the application for gadgets, for devices. You know, making something faster, run at colder temperatures, maybe longer lasting. A lot of reasons for these things, but it has to do with looking or discovering behaviors that were not seen before, and usually they do those at very low temperatures. Okay, so they run something they can't see in there, they don't know what's going on, they simulate it with particles, and they say, well, we'll call this particle A, now we call particle B. Sorry, I meant quasi-particle A, quasi-particle B. Physical interpretations made with quasies, they're all crazy. They're all irrational. Not one of them is rational. You can't simulate any invisible, intangible phenomena of nature with any kind of particle, let alone with quasies, okay? And you can't even do it with classical particles. You know, the people who use the ether, which is a bunch of particles out there, they simulate everything with vibrations of lots of particles. They call those waves, transverse waves, or what is it, longitudinal waves, and so on. It's all done with particles, discrete particles. And you cannot explain anything with discrete particles, because the big problem that particles and waves, which are made of particles, will never be able to explain is action at a distance. You cannot explain gravity. You can explain how this particle over there pulls, the word pull. You cannot explain how a particle pulls on another. And so you'll never find the word pull in any simulation with particles, ether, Dirac, whatever you want to call it, space-time, made of points, events. All those discrete particles, you'll never explain a single invisible, intangible phenomena of Mother Nature's with them. So that's the story of quasies. Okay, let me get on with these questions and comments that people made during the week. Here's the first one. A person says, if there is light, there is quantum jump, and it causes rotation of rope. His English was not so good, but we'll manage here. Also, so there is always electricity, because electricity is rotation of rope. Am I correct? No, you're not correct. Okay, so let's clarify that for this gentleman. Okay, let's find out what it is. Here it is, under the rope model. This is the difference between light and electricity is not light. Okay, here you have two models. Light is the quantum jump of an atom. In other words, it pumps back and forth. There is no particle that goes from energy level to energy level, higher energy level to lower energy level and back. None of that. What you have is a membrane, which is, in the case of the s orbitals, they are spherical. Okay, all the s orbitals are spherical, and we're just going to treat with those because they're simpler, and it jumps back and forth. By doing so, it torques the rope, and it is that torsion which we call light. Okay, is that what electricity is? No, that's what light is. What is electricity? Electricity is a row of merged atom shells. In other words, those balls that you see there, those are membranes, and in this case we simulated them again with s orbitals only. And so we bound them together, they're merged, and the whole row of atoms, okay, atoms, could be molecules also, and they spin in place, and it is that spinning in place which we call electricity. So no, the torquing of the rope is not electricity, it's the torquing of a row of merged atom shells, which we call a serpentine. Serpentine spins in situ, in place. Okay, another common question, here it is. Fellow says, how do you find out if a single homogeneous sphere is spinning? Because I talked about a top spinning the other day. We talked about it with my son, the fact that spinning means that, you know, an atom or a component or a side or whatever region, assuming it's made of a single piece, right, goes to the other side. We call that a spin. Okay, so it involves two locations of at least one region, object, atom, whatever you want to put in there. Okay, you have to monitor a single point on its surface on its equator. If the point moves about an axis of the sphere, then it is spinning. There exist 2 points where the sphere will be spinning, and this test will fail. Just make 2 tests with a single points 90 degrees apart. If you touch a spinning gyroscope, your contact point is a single point, and if your finger moves, the gyroscope is spinning. People have been brainwashed to exhaustion that experiments have something to do with science. And they want to prove the word spin by running an experiment. That's not how we do it in science. How do we do it in science? Well, this is the way we do it in science. We don't do experiments in science. Never do an experiment in science. It's only irrational people who don't understand science who do experiments in science. In science, we don't do experiments. In science, we explain them. And we do not observe. We do not gawk. Okay? Which is what mathematical physics does. No, we do not gawk. We do not observe or do experiments. What we do is explain them. Science is about explaining, not about observing or doing experiments. Okay, so here's the answer to that. Here you have your top. Okay, and do we know if that top is spinning? Well, the only way we're going to know is by defining the words. We have to know what the word spin means. Okay, we have to have a definition for the word spin. What is it to cause or turn around rapidly as on an axis? Turtle whirl, that's on dictionary.com. Maybe there's better definitions out there, but here, rotate, this gives us the idea. To cause to turn around an axis or center point, to revolve. And according to the Wikipedia, a circular movement of an object around a center or point of rotation. The point here is that if you want to define spin, you need at least two objects, 2 points, or one object at 2 locations. You need 2. Okay, and we don't run an experiment. What we do is define the word spin, and then we'll know if a top spins or not, if it meets the definition of spin. And again, here you have spinning of a sphere, and by doing so, you can see that any point that you look in there, it's going to be at 2 locations, or it's going to move with respect to another point. So that's what we call spin. Okay, you got to define spin, not do an experiment to prove spin, which is what this fellow did. Okay, here's another question, comment. There it is. It says a field is not a bunch of numbers, which I said it is, okay, the other day. It's a collection of lines. Well, what is a line? Is there such a thing as a line? I mean, it'd be nice if you drew a line if it's a physical object. Okay, there is no such thing as a line. In mathematical physics, geometry, they have a 1D line. In other words, it's made out of a single dimension coordinate vector, or whatever you want to call that. It's a number line. That's what a line is, a number line. And so a collection of lines doesn't tell us anything. You have to tell us what a line is. And a line is got an example there somewhere maybe? I should have put one up there. But anyway, a line is 2-dimensional rectangle, elongated rectangle. Line is a 2-dimensional thing. If you're going to, I mean, just look at any line that you can see, it's 2-dimensional, guaranteed, at least. Okay, it could be 3-dimensional, but for sure it's 2-dimensional. It's got 2 dimensions, width and height. No line there's no object in the entire universe that doesn't have at least 2 dimensions. Okay? All objects are 2 and 3 dimensionals. No objects that are 0 or 1-dimensional, no objects beyond 4 or beyond. Okay? So there is no such thing as a line. That's the first problem. Okay? And so lines cannot exert a force, and line of force cannot tell us anything because there is no such monster as line of force. You got to tell us what a line is. That's the issue. That's where it would be nice if you would have put that in there, what a line is. Okay, so what is a field? Well, we look it up. We look at the definition. There you have it. A physical quantity. What is a quantity? A number. What is in a quantity? An amount. It's a value. That's what a quantity is. Field is a quantity, okay, represented by a number or another tensor. Okay, so what is a field? It's a quantity represented by a number or tensor, which is a number. That has a value. Value, what is a value? It's a number. For each point in space and time. So what is a field? Number. That's what it is. And there you see down the right, bunch of vectors. That's what they are. Field is a bunch of vectors. What is a vector? Vector has, according to math, says magnitude and direction. We don't know about direction, but for sure it's got magnitude. Okay, direction, only physical objects have direction. Numbers don't have direction. Number lines don't have directions. And then here you have it in the dictionary.com. Field, the influence. That's what a field is. It's the influence. whatever influence is. And I have to separate these in pieces because people don't know how to read. They read and they don't understand what they read, so I have to kind of chop it off so they can see what the problem is. Field is not an influence, and field is, well, you could say it's an influence, but if it's an influence, obviously it's a concept. It's not a thing. And if it's a quantity, it's not a thing. And so it's some agent. That means we're not talking about the agent, we're talking about the influence of the agent. Okay, so that's the problem. Okay, and it says considered as existing. Now, it doesn't exist because you have to define the word exist in order to know what existing means. Okay, you can't say it exists, that a number exists. Not in physics. Maybe in ordinary speech, a number can exist. Okay, so, yeah, field is a number. And you might say, well, you know, there's something physical there. Field, it's got to be something physical. My two magnets, the little black round circles there, okay? And there you have it. And you say, well, what's in between here? Well, you say it's a magnetic field. Yeah, what is a field? Can we have a field without a magnet? And so you have to identify what a field is. What is in between these two? What physical object is there? And you say, well, I can't touch or see anything between these two magnets. So a field is not mediated by objects. Well, then you're doing physics with spirits. You're filling in that same space, that blank. You're filling it with ghosts, with black magic. That's what you're doing. You're saying that this is physical, right? We have two physical entities, and they're pulled together by nothing. By nothing that is between them. And you say, well, there's a field between them. Okay, what is a field? Do we have a field out here that we can take and move it around? Can you bring a field to the conference? Can you make it visible? And you say, well, I sprinkle iron filings over it and I see these lines. So what are those lines? I mean, if it's a line, obviously those are discrete lines. Now there's one line is separated from another line. What are those lines? Are they physical entities? Are they just abstract concepts that are bringing these two things together? And that's why for the purposes of physics, we have to define what an object is and what a concept is, separate those two. We can't do physics with concepts because otherwise you're doing irrational so-called physics. You're not doing physics at all. You're doing black magic. You can't move concepts. You can't say that a magnetic field is mediated or whatever's in there, those lines are just abstractions. You can't say there's no physical object there. No, there had better be a physical object there. Otherwise, we're all crazy. Okay? Otherwise, you're doing black magic. So yeah, a field is mediated in the rope model, very simple. It's mediated by threads. Okay? Real threads. You know, I mean, you know, like the thread you sew, but obviously at a much thinner level, way beyond Planck level, you know, Planck length level. Okay. Okay, another question, comment here. Here it is. Well, it says, so the thread is not a standalone object. Is it a concept? Or dependent object? My God. Here's a thread, okay? Let me show you a thread. I think this is it. There's a thread. Now, is there any other object together with that thread? I showed you that I can put a thread all by itself without any other object in its vicinity. So that's not a dependent object in the sense that it doesn't depend on another object for me to call it thread. I can point to a thread without any other object in the field of view, in the frame of reference, in whatever you want to call it. Okay, I don't need any other. There could be a single thread only in the universe. That's all there is. And we don't need to see any other object next to it to understand what a thread is. Okay, that's not the case with a field, for example. Field, you need the magnet, because without the magnet, you don't have a field. That's the problem there. You don't have a standalone field. Okay, and what is an object? Well, it's that which has shape, and hopefully that thread has shape there. You see something there. I can point to it, so clearly that has shape. Okay. Okay, here's another comment, question. Paul says, what? Says, show us a square without a drawing of it. Well, first of all, it doesn't matter if I draw it or not. I mean, what's the point of saying that I can't draw it? Drawing is not the object. The object's what you see there. It has shape on its own. It's the finished product, not drawing it or weighing it or moving it or doing anything with it. I don't have to draw it. Okay? But there I drew or took a picture of a tree. Is that not an object? Well, it has shape, and that's the definition of the word object. And all you have to do, you say, how do you call it an object? Well, I call it an object because both of those objects have shape. Okay? Both of them have shape. Does any of those two not have shape? Okay, so that's the answer the question you have to answer. And then the other issue, if you don't like that definition, you don't think that it's the valid definition, all you have to do is define the word object very rigorously and be able to defend it. Defend your definition. Get in the ring and fight for your definition. Let's see if you can. I fight for my definitions. Hopefully you can do the same. You cannot define the word object. Don't even try. Don't even put a question, because until you answer what is an object, you got to define the word object. Then we can have a discussion. Otherwise, there is no discussion. What discussion can there be if you can't tell the world what you mean by the word object, what you think an object is? I'm telling you what an object is. It's that which has shape. If you have a different definition, very simple. Put the definition on, then we'll know what it is. But defend it. Be able to defend your definition of the word object. And I've, done a lot of analysis of the word object. So, all you have to do is look at some of the previous videos, and you'll know what the arguments are. Okay, so be careful when you want to define the word object. It's my greatest contribution to science, the definition of the word object. Okay, I'm an expert on the word, by the way. I claim to be an expert. I have a definition for nothing now. Oh, good. Good, we have a definition for the word nothing. Nothing, object that doesn't exist, that you present physics on. Okay, now all you have to do is define the word exist. We have no idea what you mean by the word exist, and it turns out that you have to define the word nothing and the word object or something before you define the word exist. Okay, so we need to know what the word exist is, because otherwise, you can't even start. And before you can define exist, you have to define what an object is, and the antonym of object is nothing. So those two words always precede really the word exist. So you can't say you're going to use the word exist to define the word nothing. You have to define object and nothing before you define the word exist in physics. Okay? That's the sequence. It's an unavoidable sequence. Otherwise, tell us what you mean by exist, and we'll have an idea. Okay? Hopefully you don't use the antonym of nothing to define the word exist then. Okay, Phil says the thread is a concept in the context of one universe. Yeah. One guy answered, universe in itself is a concept, though. And he took the words right out of my mouth. So let's clarify that to make sure we understand why that's the case. Okay. And so what we have to do first is define the word concept. We have to know what a concept is. An object is that which has shape. What is a concept? A word that embodies or invokes two objects. In other words, it's a relation. Or two words treated as objects. For example, the word universe. Universe is comprised of two words, space and matter, or objects. Okay? So we have objects and we have space. We call that the whole thing, which is not a thing, it's a concept. We call that universe. So universe is a concept because we're treating space as a physical object. We're assuming momentarily that we have two things there. We have the object, or the objects, plural, and we have space. We have two objects, we have a concept. Okay? So that's why the word universe is a concept. Yeah, it is. So the single thread, remember what the single thread is and what it represents. First of all, here we have the single thread, and I put two of them there because people are going to say, well, does the thread exist? Does it have location? I showed that the other day. Yeah, here you have the thread. You have two threads, so they have location because one has distance with respect to the other. No problem there, okay? The thread exists. If you're going to talk about thread, the only context for the global thread, the universal thread, is with respect to another thread. Otherwise, we have no use for the thread itself. Locally, we use the thread only for constructing atoms, the membranes, the electron shells, and for magnetism. Other than that, we have no use at all for the thread. Okay, and what do those threads represent? Again, they represent two universes. That's what the thread represents. In other words, all the matter in the universe is represented by those threads. The thread underlies all the matter in the universe. Okay, so that's the foundation of the rope model. Okay, we don't call it the thread hypothesis, we call it the rope hypothesis because we're interested in the local functioning or behavior of what? Light, gravity, all those things are mediated by a rope. And only in the case of magnetism is it mediated by the thread, but not by the global thread. It's mediated by many threads locally. Okay? Many portions of that global thread, of that universal thread. So we have no use for the universal thread. People who harp on the existence of the thread, all they're talking about is the existence of a second thread. That's the only context of the existence of the thread. Otherwise, it just underlies all matter in the universe. Okay, and here's another question, another comment. Fellow says, he says, if there is nothing between two objects, they are one object, right? Yeah, essentially there you have two cubes, two elongated boxes, whatever, cubes. And on the bottom you have a more elongated box. Okay, so again, what you're talking about there is something made of a single piece. And again, it's an idealized situation. Okay, and all we're saying here is that in the case of the one on the top, you have two boxes. And hopefully if you're talking about two, they're separated by something, which is nothing, which is what? Ultimately space. Okay? And in the bottom case, it's not separated. So we're assuming we have the same volume, but it's a single piece again. So there is no space in the middle of that piece. It's made out of a single piece, and yeah, it's just a different object. Okay? And again, these are idealized objects. We treat them as if they were made of a single piece, like if God made them, just of a single piece. So again, these are idealized situations. Okay? Yeah, you have to have space between any two objects. And remember, like I said the other day, if you have a chair and a table, we see them in our everyday world as two distinct objects. But keep in mind, all the atoms from the chair are connected to all the atoms of the table. That's going to be the light that goes from one object to the other, and it's going to be the cause that underlies gravity between these two objects. You have to have a physical mechanism to explain gravity. You can't do that with abstract concepts. You can't do it with magic. Okay, you got to have a physical object. What is a physical object? That which has shape. Okay, another common question. Fellow says, is the black in between a vacuum? Another fellow answered, vacuum is nothing. So essentially he answered the question for me, saved me some work. Vacuum is the black stuff. So you can't have black stuff between two vacuums or vacuum between two black stuffs because it's all black stuff. It's all vacuum. It's all space. It's all nothing. Nothing. What is nothing? That which doesn't have shape. Nothing is the opposite of something. What is something? That which has shape. We're done. Now we can use those words consistently, rationally, in a scientific dissertation or one of physics. Okay, another common question. Here it goes. Fellow says, is space nothing without shape? That could be interpreted in two ways. The question is whether space has shape itself, and it's almost like a word wizardry there. You're saying, Here we have space, which is that which doesn't have shape, and you're saying is it nothing without shape? Well, yeah, that's the definition. And the other one, interpretation could be if there's nothing within space, to use that term. In other words, assuming space forms the backdrop to every something out there, that which has shape. If you remove that, if you remove all the objects from the universe, is space still nothing? Is the space not have shape? For that, we go to the definitions, period. Just follow the definitions, you won't get hurt. Space equals nothing, they're synonyms, okay? Space, that which doesn't have shape. Okay, very straightforward. So just follow the definition, nobody gets hurt, okay? Promise I won't send Tony in there to collect on these definitions. In other words, space doesn't have shape with or without something being in it. Okay? It doesn't matter. Okay, just follow the definitions and we promise we won't hurt anyone. Okay, here's a couple more questions. First one. Fellow says what? Says quantum particle is indeed wave-particle duality, and if it's about waves, the equation of waves can always be represented using complex numbers. Yeah, we can represent the wave, particle wave, as they do in mathematical physics, with an equation, okay, with a function or whatever. But what you're looking at when you're talking about wave, you're talking about vectors. Wave is a misleading term because people think it's a noun. It's not a noun for the purposes of physics. In ordinary speech, it's a noun. You can talk about the wave. Not in physics. In physics, there is no such object called the wave. Okay? Wave is a verb. Wave is action, pure action. What is waving? They never figured that out. They say it's the ether, a bunch of particles. That's what's always been assumed. For the last 400 years at least, the ether has been a bunch of particles that are waving up and down. Why they wave up and down, why one particle follows the other, we have no idea. They never explained that. They cannot explain how one particle pulls or compels another one to do anything from a distance. So they cannot explain it with particles. Again, the particle hypothesis cannot explain any phenomenon, invisible, intangible phenomenon of Mother Nature's. So what is a wave? Wave is just a bunch of vectors that they've set in motion. What is a vector? Magnitude, essentially. They say it's direction, but it's just magnitude, just a number. What they're moving is numbers. What you're staring at is an arrow that they put in lieu of a number. They put an arrow there and you say, okay, now I understand because I can see something moving on the screen. No, you're staring at numbers. That's what those arrows are. Those arrows are just numbers that are moving. So it's a mirage that you're staring at. You're not staring at anything that is real. What they've done is they replaced the numbers with arrows. They call them vectors. They put them in motion. They put it as collective motion. What? A quasi? Another quasi? Is that what a wave is? And they have these vectors and they're oscillating. You say, okay, now I understand because I see something moving on the screen. No, you're staring at a bunch of numbers, bunch of vectors. Keep that in mind whenever you look at that sine wave that they show there moving. It's ridiculous. It's because they have no idea what's out there in the invisible world of Mother Nature. That's why they have to do this. Okay, I think I have a final question here. Or issue. Fellow says, survey says, there it goes. Says, I asked about invisible, intangible, physical object, double rope, single thread, passing through each other. Invisible, intangible, physical objects? What? Yeah, because an object is not that which you can see or touch. So visibility and tangibility have nothing to do with the definition of the word object. The word object, that which has shape. Again, he who has a better definition, better mousetrap, hey, just put it on there and be able to defend it. I mean, it's not an issue of copying and say, well, I found this in the dictionary and I'm going to follow that because everybody in the universe follows that. Yeah, I don't care. If you can't defend it, it's worthless. Okay? So it doesn't matter how many people stand behind you. It's just you and me, buddy, on this island. Okay? So you got to defend it. And if I knock your definition out, you can't use authority and say, well, this is what everybody else believes. That's worth zip. Okay? And the question is, can you see or touch the mediator of gravity? You know, I let go of the pencil, the pen, okay? I can't see or touch anything here other than the air, but we could do this on the moon, you know, as it's done by Neil Armstrong. No, not Neil Armstrong, one of these other guys. And they let go and it falls always to the ground. But we can't see or touch anything here other than the air here on Earth. And so what do you propose? You propose that it's done by spirits, black magic? Is that how gravity is done? What pulls the pencil to the floor? Why doesn't it pull it to the sky? What are you going to use? A concept such as mass? A concept such as gravity and say gravity pulls it down? So far you haven't explained anything. All you did is give a name to a description. You say this description that things fall down, we call it gravity. Great. And what pulls it down? Like, you know, I want to pull on a horse, and I can explain that to you. I said, well, I tied a rope around the horse's neck, and I'm pulling on it, and now you understand the mechanism. The way I pulled on the horse is with the rope. But imagine I had no rope, and I go like this, and I'm pulling on the horse. And the horse, you know, responds to my hands moving back and forth. Now you ask, well, how did you do that, Bill? What invisible, intangible object did you use to pull on the horse's neck? What am I going to say? I pulled it with gravity, I pulled it with mass, I pulled it with force, with field. No, I got to put a physical object there. I got to put a rope, I got to put a wire, a cable, a string, a thread, some elongated object. Maybe a coaxial. I got to put a physical object between my hands and the horse. I can't say I pulled it by magic like quantum does. So yeah, it better be a physical object. And you say, well, but I can touch the mediator between your hands and the horse. Yeah, you can. But Mother Nature does it with invisible intent, does the same thing with invisible, intangible objects. That's where the trick comes in. So whatever you use, it better be invisible and intangible, and that doesn't outlaw the word object, because the word object has nothing to do with see or touch, with tangibility or visibility. Object is that which has shape, not that which you can see or touch. So see and touch have nothing to do with it. And can you touch the mediator of magnetism? Is the agent that does magnetism a ghost? Is that what you propose? We're going to do this with what? With ether. We're going to do it with I don't know, plasma, what other waves? What invisible entity do you propose? And it better be a physical entity. Otherwise, you know, you're going to use a concept. All you're doing is giving a description. So you can't use the word force. You can't use the word energy. You can't use the word, mass, charge. Any of those words, those are all concepts, mathematical concepts. You can't say you're going to pull on something with charge or with electricity or with plasma. All those are concepts. None one of those is a physical standalone object. Okay? In fact, they're all concepts in motion. Objects in motion. Okay? What is plasma? Plasma is ionized, ED, right? Gas. That's what plasma is. It's something in motion. What is a field? It's vibrating something. Whatever's vibrating in there, we don't know, right? But field is the vibration of that something. Again, another quasi. All these quasies. Okay, so what do we respond to this gentleman? Here it is. We have the single piece and the segmented piece. Okay, and some people who even like the rope model, they say, well, how does a thread go through another thread? How does a rope go through another rope? And what they propose is that the thread is segmented. Okay, and so we have a problem with that because, see, you can explain this with, how maybe a thread goes through another. Let me show you this. Okay, you can see how a thread goes through another if they're segmented. But you created a monster because now you cannot explain the integrity of the thread. How does one particle, segment, or whatever you want to call those individual discrete things, okay, pull on another one? How does one of those red balls pull on another red ball? Why does the second red ball follow the first red ball? And that's only the first of your problem. You got a lot more problems than that by creating segmented things. Okay? No, you cannot use a segmented thread if you're going to follow the thread model. You have to assume that the thread goes through another thread. It has that property. You can think of it maybe as crossing two light beams. I mean, here it is. I showed it the other day. Here you have a light. Let me just point it. Okay. Laser pointer. I just put the light on. And, you know, you have two lights, essentially, and they cross each other. They don't bound the light, whatever light is, those things are not interfering with each other. They go right through each other. And so the question is light mediated by a physical object? So what is a physical object? That which has shape, not that which you can touch or see. So it has shape, whatever is in there, but it doesn't have the ability to touch the other one. Now we can make sense of what Mother Nature has out there. We have a physical object that underlies light, in this case the rope, but these ropes have the ability to go through each other. And that's what people say, what do you mean? Yeah, we don't see that in our macro world. But again, light goes through light. Let me show you one more time. Here, light, okay, one. Let me show you this one. It's a little bigger. Okay. 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 Here it goes. We have these two lights. Let me put this one on. Okay. And light goes through light. There are no photons, you know, bouncing off of that. Okay. Light goes through light, and so you got to explain how light goes through light, and what mediates light. Is light mediated by a physical object, by an object, something that has shape? And if not, then what is it mediated by? By ghosts, by phantoms, by spirits? Hopefully there is a physical entity mediating light. Physical, that which has shape. What are we proposing? It's a rope. What are we saying? A rope interconnects any two atoms, and a rope has the ability to go through another rope, just like light has the ability to go through light. At Mother Nature's microscopic level, the ropes do not have the ability to touch, at least at that level. Okay? Touching, as I said, invisibility, require accumulation, many. You know, you can't see one atom, but you can see the table. And the table is made out of atoms, each one of which you cannot see. So the only way to see a table is having a bunch of them. And the same thing happens with a rope, and the same thing with threads, at least for touching. Visibility is a different issue. Again, when you're talking about something so microscopically thin that there is no way you can ever see a thread or a rope. You know, it's beyond human ability. Anyways, with that,